Hey, it's Dr. J. Today we're going to learn about average value. In particular, since this is a calculus class, we've been talking a lot about functions, the integrals, definite, indefinite, derivatives, all sorts of things that we learn about functions in calculus. We're going to focus on the average of a function. It is related to what's called the arithmetic mean. So arithmetic mean is a fancy way to say the average of a set of numbers. So suppose we had a set of numbers. All right, let's call them A1, A2, A3, and there are n of these numbers. Well, you probably already know this. The average is the sum of all these numbers divided by the number of numbers. So it's the sum of all the values divided by the number of values. Or how many values are there? So if you were just telling this to your friends or family, or if you're just trying to explain what an average is to somebody that didn't understand a mathematical, principle, you could say, well, it's actually quite simple. You just add them all up and divide. Yeah, that's kind of the basic way to explain averages. Well, in calculus, we're going to do something very similar to this, but instead of adding up numbers, what we're going to do is add up rectangles. So we're going to call this the average value of a function. We're going to add up infinitely many rectangles and then we're going to divide by the number of rectangles, by the width of the interval, which is kind of like the number of rectangles, but I'm going to say width. So this formula here will turn into this formula. So suppose we start at A and we end at B. And I'll leave this here for a minute, but it's going to have to go eventually. So this time, instead of saying A1, A2, A3, I'm going to go from A to B. That's the interval. We'll say the interval AB. And then we have our function, f of x. There's our function. And then we have the rectangles. I'm not going to draw infinitely many rectangles. It's going to be just like it was in the previous lectures. It's the limit as n goes to infinity. Where n is the number of rectangles. So this is the limit as n goes to infinity. The area is the limit as n goes to infinity of the sum from j equals 1 to n of f of xj delta xj. Yeah, the Riemann sum. So that gives us the area. And we're going to take this area, the area under the curve, And instead of dividing by n, because we can't divide by infinity, right? There's infinitely many rectangles. So instead of dividing by the number of values, what do you think we're going to do? We're going to divide by the width of this interval. The width of the interval is b minus a. That's how wide this interval is. So we have the limit as n goes to infinity of the sum from j equals 1 to n of f of xj delta xj all over b minus a. Or I like to write it like this: 1 over b minus a times the integral from a to b of f of x dx. All right. I don't really want you adding up the area of, 27 rectangles or even 6 rectangles, not to mention adding up the area of an infinite number of rectangles. But I still want you to understand that when you find this integral, the definite integral, you are essentially adding up an infinite number of heights, right? Remember, each time you plug in an x, you get out a y, which is giving you the height, right? And then you have the width of each rectangle, and then you're adding them all up, and then you're dividing by the width of the entire interval from a to b. All right. So this is called the average value of the function, or f_av. Let's do an example. So f of x is 1/5 x plus 6. Find the average value on the interval 2, 9. Okay, so let's go ahead. This is example 1. We'll start with the integral from 2 to 9. So I usually start with just this part. Now you could do the whole thing all at once, but I've kind of laid it out like this so that you can do it step by step. So from 2 to 9 of 1/5 x plus 6 dx. It's just another excuse to cover the fundamental theorem of calculus. All right, so that's going to be equal to, well, what's the antiderivative of 1/5 x? That'll be 1/5 x squared over 2 plus 6x. All right, remember, you can ignore the 1/5, not really ignore it, but pull it outside, and then take the antiderivative of just x. So you add 1 and then divide by 2. So that's going to be x squared over 10 plus 6x evaluated between 2 and 9. Okay, so we're going to get 9 squared over 10 plus 6 times 9 minus, be careful here, I'm just going to use some brackets, 2 squared over 10 plus 6 times 2. So 81/10 plus 54 minus 4/10 minus, so be careful with negatives. That's why I had this extra set of brackets here. 12 me come up here to put my final answer. I've got 81 tenths minus 4 tenths, so that'll be 77 tenths. And then I got 54 minus 12, which is, what's 54 minus 12? 42. I'm going to switch over to decimals now. Round to the nearest tenth, so I don't need to round this. 77 tenths is just 7.7. So I'm going to get 49.7. So that is the area under the curve between 2 and 9. It's not the average value yet. I'm just going to put a little picture over here to give us something to look at while we're doing it. This graph is not to scale. So here's our F. It starts at y equals 6. We're starting at 2. So that we're looking at this rectangle right here. I always say rectangle, but you don't actually draw a rectangle. It's an infinite number of rectangles from 2 to 9. Just gives you something to look at while we're doing the problem. All right. So the 49.7 represents the area. 49.7 under this curve. And again, my drawing is not to scale. It's just to give you something to look at. All right, so then FF. Here's B. Here's A. So FF is 1 over 9 minus 2 times 49.7. Or you could just say 49.7 over 7. Because 9 minus 2 is 7. I was able to do all of this without busting out the calculator, but I'm going to go for it now and use the calculator. So 49.7 divided by 7, 7.1. Ah, now I feel silly because 49 divided by 7 is 7, and 7 divided by 7 is 1. I should have been able to do it, but that's okay. I'd rather be right than be brave. You get the idea? So 7.1. It's actually interesting. The 6 here really didn't matter. So you might wonder, why did he put the 6, right? Why put the 6 there? Well, I was just trying to show you that the function relates to the picture. The 6 is the y-intercept. It doesn't actually show up in your calculation anywhere because we didn't start over here at 0. We started at 2, so we're kind of far away from the 6. But it's interesting to see that because your final answer is above that number. So it's 7.1. So here's 6. Here's 7.1. Right? The average value always cuts right through the area. What's even more interesting, and I'm going to do this in example 1 because this is probably the only example in which the picture is so nice that I can't resist. If you took this little area here, right, and you cut it off and put it right here, you would get a rectangle in which it goes from 2 to 9. This little piece would fill in right here. And then the rest of it is already down here. And this will happen with every problem. They're not all going to be as easy to draw as this one. This is example 1. It was nice and clean. But whatever goes above the average, right, you can think of cutting it off and redistributing that value into here. And then you just have a rectangle in which the new area is the same as the old area. It's still 49.7. Right? So the average is basically saying, what is the ceiling of this function in which if I made it all the same, right? Uniform distribution. Everybody gets exactly the same score if you think about it as a test, right? Imagine if I did that in a math class, right? I take all of your test scores, right? And then I redistribute the wealth. So those of you that got a 95 would be benefiting those of you that got a 62, right? And then I redistributed and gave everybody a 71. I know this number is not really 71, but right, you get the idea. So the folks that were down here in this deficit area, they're going to get paid by the people that were above. It's a redistribution of the value. And you can see very clearly that this rectangle, the width is 7, the height is 7.1, and the area is 7 times 7.1. I hate when I use dots and decimals, but you get the idea here. I could use an old-fashioned X for times, which I rarely ever do. And I'm still going to get 49.7. So this rectangle will have exactly the same area as the original problem. And that is the entire concept of average value. Well, back in the 90s, I would have said, all right, class dismissed. That's all you need is one example. Go read the book and do all your homework, and I'll see you on Monday. But this is 2024. I'm on the internet. I've got lots of examples to do to kind of guide you through the process. So let's try another one. So f of x is negative 6x squared plus 96x plus 46. So let's find the average value on the interval 8 to, 12. So we'll do the area. That'll be the integral from 8 to 12 of f of x dx. Just being lazy. Instead of writing all of that, I could just say f of x dx. All right, take the antiderivative, so it'll be negative 6x cubed over 3. 96x squared over 2. This is the calculus part now. I'm not really going to review that too much, but you're going to see a lot of these today, where you're just using the power rule of antiderivatives. Instead of going down, the powers are going to go up. And then we're going to evaluate that between 8 and 12. So I got negative 6 times 12 cubed over 3. I'm not going to try to show off. I'm just going to plug this into my calculator and see what I get. Oh, I can simplify a little bit here. Why don't I do that? I will show off a little bit. If possible, simplify first. I made all these numbers nice. 96 divided by 2 is 48. It'll save you a little bit of work later. If you don't simplify, it's not going to cause you to get the wrong answer. It's just going to make you work harder. Oh, and then don't forget the 8. So you're going to go minus, and then be careful with signs. So negative 2 times 8 cubed, 48 times 8 squared, and 46 times 8. I'll come up here to put my results once I do them in the calculator. So, all right, so we got 8 cubed. I think I have a cubed button on my iPhone calculator. That's 512. I don't know why I did that one first. What the hell? Let's just write down everything that I got. 8 squared is 64. 12 squared is 144. I meant to do 12 cubed. That was the one I couldn't do in my head. 1728. All right, I like to do all the powers first. Okay, so now I'm going to go traditional and just go left to right. So negative 2 times 1728. I bet you love watching me do this. Plus, I'm going to write that down. This is where having a traditional scientific calculator might be better. You might be able to just type all this in and get it done. Feel free to fast forward the next couple minutes while you watch me do this painstaking calculation. 48 times 144. 46 times 2. I think I do that in my head. 92. All right, I got that one, that one, that one. Let's see. 2 times 5, 12. I knew that. Oh, I should mention the negative, I might as well just get rid of that now. That's going to turn to positive. So positive 1024. This positive is going to turn to negative. 48 times 64. I show all these calculations because I find that when I grade papers, like if you were in my classroom, I would see that you might do all of the calculus correctly and then screw up the arithmetic. And I do the same thing, you know. If I make a mistake, it's probably some very basic arithmetic mistake. Rarely ever do I see students making major calculus mistakes. So check your arithmetic. That's why I like to write everything out in absolute detail. All right, so I've got negative 368. I'm just gonna, it doesn't matter the order as long as the signs are right. And then negative 3072. And then positive 1024. If you really want to be safe, you go from left to right, but just be careful with the pluses and the minuses. So plus 92, plus 6912, minus 3456. So my final answer is 1132. 1132 square units. You could just type 1132, but it is technically a measure of area. Since we're not using meters or feet or centimeters, we have 1132. All right. And then, so now to find FF, you take the area and you divide by B minus A. I'm going to write the formula down one more time for you. Type of thing you want to have handy when you take the next test. You know, you don't want to go digging for this formula. Have it out and ready to go. So I got 1 over 12 minus 8 times, now I already did this, 1132. So 1/4 times 1132, or simply 1132 divided by 4. Now, I could have done the 1/4 a long time ago and not even written down the 1132, but there are some questions that ask for both. So you don't want to skip over this and then have to backtrack to find it. So I always find the area first. I think about it, make sure it's right, and then I find the average value, which is 283. This one's a little tougher to draw, so I'm not going to. But if you're curious, it's an upside down parabola. It goes up very, very high. And then the average kind of cuts it like this. Yeah. And then we were between, here, look at me. I said I wasn't going to do it, and I did it anyway. We were between... we were between 8 and 12. Yeah. So that's sort of a rough idea of what the graph would look like. So you have this area. All right, you have this area. That's your 1132. And then you got this average. I actually put the average a little bit too high. A little bit too high. So you got this sort of average right here. Oh no, I put it too low. That's what I did. You guys just got to tell me to stop. Just stop, Dr. Jordan. Just stop. I don't know. I don't want to stop. Why do I have to stop? I had the average right. It's right about there. So the FAV was 283. I don't really know how high that is. I haven't bothered to calculate it. It's definitely higher than 283, right? And then if I made this rectangle, here, let me, if I made this rectangle and I filled in all of this gap right here, my drawing is not very good, I'll have to admit. It's slowing me down quite a bit because I'm just so OCD about it. I would fill in this missing spot with all of this. Yeah. And I would have a rectangle that's 4 units wide, 283 units high. Yeah. And so this, you would cut this off here, and you would just have this box, right? Although it would probably look more like this. So drawing is not to scale. Right. My parabola was terrible. In reality, the parabola looks like this. It's like a tall, skinny parabola, but I blew it in my very first sketch. And if you multiplied the average value, which is the height, times the width, you should always get the same as the area, which is why it's always a good idea to pause when you have the area, because that's kind of a way of checking that your final answer makes sense. Okay. We have a theorem, right? I only have 2 examples, and then we can get right into our theorem. This is called the mean value theorem. Mean means average. It doesn't mean that it's not very nice. It's being mean. We're finding the average, right? If f is a continuous function, on the interval AB, then there exists at least one C. So there exists at least one value. I always put the at least one in parentheses because it's typically just one, but there could be more. So it's at least one, right? Such that f of C is equal to f av. Again, the proof, I'm not really going to prove it. I'm just going to sort of verify it using the idea that I just talked about. Suppose the average is right here. I'm trying to get my drawing just right. So the average always cuts through the graph, through the ceiling of the curve. This is your value C. And C is always between A and B. All right, so C lies somewhere in between A and B. Now, this theorem just guarantees that it exists. It doesn't actually find the C for you. And you can probably tell by the picture why there's at least one, because sometimes the curve might go like this, right? And might hit the average more than once. It's possible. It could hit it a whole bunch of times, right? Depends on what the function is. But we're guaranteed no matter what that we're going to get at least one of these values that lies right in the middle. In real life application, you might say, well, again, go back to the test. If I give a test to the class and you get a whole bunch of different grades, and then I say the average is 76, it does not mean that at least one person got a 76, right? Because grades are not continuous, right? In grades, one person could get a 62, one person could get a 93, somebody else could get a 74. If there's a continuous function, it means that every single possible grade was achieved. So 60, 61, 62, 63, and even all the decimals in between. 61.5, 73.8, 91.5. That's not realistic in the real world application, right? Now we will do some business applications, and I'll explain more about how these concepts can be related. But for now, we have the mean value theorem. It's very abstract. We're assuming we have a continuous function, and I'm going to next ask you to find the value of C. At least you know where to look. It's going to be somewhere between A and B. All right, let's do an example. F of x is 6x to the fifth. On the interval 3, 5. Find C such that f of C is equal to f av. All right, so we got to first find f av. Find the average of the function. So that'll be 1 over 5 minus 3 times the integral from 3 to 5 of 6x to the fifth dx. I could do this in steps. I probably will at some point. So this is my width of the interval. The width of the interval is 2. You could also say divided by 2, but I just say 1/2. We're dividing by the width of the interval. Hang on to that for a minute. Don't do anything with that. And then work on the antiderivative here. So that'll be x to the 6th. Oh, that's nice. technically it's 6x to the 6th over 6. Yeah. We add 1 and then divide, and then the 6's will cancel. So that's nice. I think I planned it that way on purpose because I just want to give you an easy start with the mean value theorem. So 1/2, and then I got 5 to the 6th minus 3 to the 6th. So 5 to the 6th power, 5 times 5 times 5 times 5 is 15,625. 3 to the 6th power is 729. 729. And again, you could say times 1/2, or you could just say divided by 2 means the same thing. 15,625. We'll subtract those. We'll get 14. Some change. 14,896 divided by 2. 7,448. If you wanted to pause and think about it, the 14,896 is the area, right? If I were to draw this curve, and then the 2 is the width, right? And so that's our average value. All right, now we got to find the C value. We know it exists, and we know it's somewhere between 3 and 5. The theorem doesn't solve the problem for you. It's really just meant to regulate your approach. And if you get a number that's not between 3 and 5, well, there's got to be a problem, right? Because we know it's got to be between 3 and 5. If for some reason we get multiple solutions, which that might happen, we're only going to pick the ones that are between 3 and 5. All right, so now we want f of c equals 7,448. So 6c to the 5th equals 7,448. C is just a value of x, really, right? You could just use x, but then at the end, you'd have to switch it to a c before you tell me what the answer is. Divide by 6. The main mistake I see on these problems is people will use the wrong function, right? Or use the antiderivative, or God forbid, the derivative. 7,448 divided by 6. No, you're going to have to round. We'll wait to round. Round to the nearest tenth. Unless otherwise specified. This is kind of our standard. I think when we get to the money problems, we'll either round to the nearest penny, nearest cent, or we'll round to the nearest dollar, depending on the problem. So C will be the 5th root of this number. I just keep it in my calculator and then I round it when I'm done. So the 5th root. 4.15, so 4.2. All right, so this is your FF, and this is your C. I'm not going to check it, but you can check it. If you took 4.2, make sure it's between. Yes, it is. Right. And then you could also make sure that if you plugged it in, do you get approximately 7,448? I'm not going to do that for you. You will. Because we rounded, you won't get exactly 7,448, but you'll get something close to 7,448. All right. I got 2 more, and then we're going to move on to the applications. If we have time, or if my battery doesn't die before we get there. I think I want to do one more of these because I want to emphasize this whole at least one thing. You might get more than one value. Just to show you that there could be more than one answer. And let's use another function, a different type of function. This one's actually much simpler, even though it's a much more common problem on the interval -1 to 9. And this one makes for a pretty good graph, much easier to graph than some of the other ones. Although not that the other ones were hard to graph, I didn't do a very good job of it. This one I probably could do a pretty good job of if I try. I don't know. We'll see how the time is going. For now, just imagine the letter U. This is a classic algebra 1 parabola. Basic algebra parabola. All right, let's go ahead and do it. FF. I'll give myself a little more room. FF is 1/9 minus -1. Be careful. I have seen people do everything right, but then they'll go 9 minus 1 and they'll get 8. And that screws everything all up. The integral from -1 to 9 of x squared minus 6x plus 13 dx. So that's 1/10. 9 plus 1. And then the integral, so we got 1/3 x cubed. Yeah. Or you could say x cubed over 3. We got 6x squared over 2. I'll probably simplify that to 3x squared. And then 13x. And now we just start plugging and chugging. So we get 9 to the 3rd over 3 minus 3. I'm just simplifying that. Times 9 squared plus 13 times 9 minus, oh God, double set of brackets. I got my sort of outer brackets and inner brackets. You could change them up if you like. I'm not going to. You could use different styles of brackets if you like. You could also just use parentheses. I'll just do that. You got to use something, otherwise the signs will end up all messed up. So that you get -1 to the 3rd over 3, -3 times -1 squared, and 13 times -1. And again, if you've got a fancy calculator, it doesn't even have to be very fancy. It's one thing, the iPhone, it's nice, it reads nicely, it's got big screen and everything, but it doesn't do multiple operations very well. It's pretty old-fashioned. It just does one operation at a time. Even though you have this fancy keyboard here. It does have parentheses, though, so you could use those parentheses. I don't know if those come out very well on the screen, but I don't know. You kids, you probably know more about these things than I do. So I got 9 to the 3rd divided by 3. I got 9 squared times 3. So 81 times 3. Oh, what do you know? Those cancel. I should have seen that a long time ago. I got 13 times 9. I'm tired. I can't do that in my head. 117. I got -1/3. I can do that in my head. I got -3. Be careful here. It's -1 squared and then times -3. So it stays a -3. And then -1 times 13 is just -13. I'm just coming up here to put my results. So I got 1/10 times 117 plus 1/3. Yeah, negative. So that's going to turn into a plus 1/3. Plus 3 plus 13. I'm running out of room, so I'm going to do plus 16, which is the 3 and the 13. They're both being added now. Again, most mistakes are going to be with your negative signs, not being careful with them. And, you know, we're getting to the end of the game here, so you really got to stay on it about that. So I got 117 plus 16 plus 1/3. Oh, God. I'm going to round anyway, so I'm going to go plus 0.33333333333 like that. So I got 133.333333. Or you could say 133 1/3. I don't care. And then divide that by 10. I'm going to round it anyway. So 13.3. So that's my FAV. That's my average. All right, pause and think about that. Make sure there's no mistakes. Double check. To double check the numbers, double check the signs. This is not the C yet. This is just the average. This is where the picture would really come in handy because you would see that it kind of looks like this. So there's your Y, there's your X, there's -1, there's 9. You have a parabola that kind of looks like this. Right. And it's not perfect, so it's more like this. So this side is much taller than this side. Again, I'm really not spending a lot of time on the graphing. We already did a whole chapter on graphing. You could go through all the techniques. You could find the minimum. You could whatever. It doesn't have any inflection point. It's always concave up. You can use all the stuff that you learned previous or even just basic algebra. You have online graphing software. Try Desmos or something, you know. I know there's a bunch of other ones out there, but I still use that one. It was the first one I ever discovered. You can see what the shape of the curve looks like. It might even let you graph the shaded region if you're really clever with it. All right. And then the 13.3 should make a little bit more intuitive sense, right? It's going to cut through the graph like this. So there's your 13.3. It always cuts through the area somewhere. So if this line misses the area, then something's got to be wrong. All right, it's got to be some kind of mistake. All right, and so now you can kind of see what we're looking for, right? We're looking for all the values of C. So we're looking for this value and this value. So it looks like there's going to be 2 C's. I mean, just based on the picture. Now, you could do it blindly without looking at the graph and just trust your answer. That's fine too. So f of C equals 13.3. So C squared minus 6C plus 13 equals 13.3. Again, you could just leave it as an X. It's not going to make a difference. In fact, you might like that better. I already wrote C, so I'm sticking with it. C squared minus 6C. Subtracting 13.3, I get 0.333333333 0. This is not a factorable equation, I don't think, so I'm going to use the quadratic formula. It says round to the nearest tenth again, so C is going to be negative B, negative 6, a little algebra review, plus or minus the square root, negative 6 squared minus 4 times A times C. Hope I'm not going too fast. If you haven't had algebra in a while, all over to A. Algebra review quad form. Quadratic formula. Negative B plus or minus the square root of B squared minus 4AC all over 2A. Bum, bum. Okay. I might regret having rounded it. I might wish that was a third instead of 0.3 because I am losing quite a bit of information by rounding, but I'm going to take my chances. If you do this with a rounded decimal, it's homework and it somehow marks it wrong and you're quite sure that you did it right, try using more digits, or use the exact number, 1/3 here, because this is 1/3. The 0.3, when I subtracted it, it just left me with 0.3, which is 1/3 rounded. Again, I'm taking my chances here. It's already almost been an hour, and I haven't even done any business math yet. So let's get into it. I got C equals 6. Yeah, negative 6 is 6. Plus or minus the square root of 36 minus, which will be plus, 4/3. 133333333 all over 2. That's 4/3. Is it? No, it's not. Yeah, it is. 4 times 0.333333. 4 times 0.333333. Yeah. It's the same as 4/3. Yeah. Now, again, I'm approximating now. So 6 plus or minus the square root of 37 and 1/3. So I've got my 37 and 1/3, or approximately 37 and 1/3. I'm taking the square root. 6 plus or minus 6.11 blah, 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 divided by 2. Which is 12.11 divided by 2, or negative 0.11 divided by 2. So this one's going to be 6.1. I'm rounding again. It's 6.055. So I'm rounding. And then this one is negative 0.11011. It doesn't matter. I'm rounding. Divided by 2. Negative 0.1. That's as close as I could get. This one's kind of sketchy because you might actually get something smaller than 0.1, but it's 0.055, which is why I'm really happy that I kept a couple extra digits. Otherwise, if I would have thrown away that digit, I might not have been able to get it rounded appropriately. So that kind of makes sense here. This one's negative 0.1. It's pretty close to the axis. And then this one over here is 6.1. And those are the two values of c in which the function equals its average. Which is not realistic in terms of, well, it's realistic in terms of continuous functions, but in the real world, not everything is continuous, right? You don't have every possible value. So, that number could maybe not even exist in the problem that you have. But we still have a calculation that tells us where it should exist if it was there. Doesn't look like I'm going to have time to get to the business math today. But I do want to cover an interesting fun fact before we do business. So this is your fun fact of the day. I'll post the business applications in a supplemental second video here. Fun fact of the day is about the logarithm, the natural logarithm. Yeah. ln of x. Here's a fun fact. If you take the function 1 over x, it's also known as the reciprocal function. It's not a very good graph, but you get the idea, I hope. So this is x, this is y. Yeah, as x approaches infinity, y approaches 0, right? I think we've seen this function before. And you start at 1. So, I should draw my graph to scale here. I'll draw my graph to scale. Might as well. Whenever I draw a graph, you should wait until I've finished it before you try to draw it in your notes. So there we go. My graph's to scale. So if you start at 1, that point is 1, right? 1 divided by 1. And then you go all the way to some value b, where b is greater than 1. So any number bigger than 1. And you find this area here. Here's your fun fact of the day. The area is the ln of b. ln is the natural log. And when I first saw that, I thought, oh, okay, seems reasonable. Didn't really question it. But the longer and the more I was exposed to it and the more I thought about it, I realized what an amazing fact that is. How amazing that is. You don't get this type of relationship very often in mathematics, right? In fact, you can kind of think of, if you really want, sort of a very obscure way to think about the natural logarithm, right? We always think of it in terms of, exponentials and the natural base e, and I did a whole, lesson on it. But if you think about it, the area is exactly the definition of the natural log. If you think about it, you really think about it. And so what this means is that the integral from 1 to b of 1 over x dx is the ln of b. Why is that so amazing? Well, if you didn't have a calculator, all right, if you didn't have a calculator and you wanted to figure out what the natural log of some number was, you could draw this graph very carefully, right? With a piece of graph paper, maybe a ruler, maybe a nice grid, and you could measure things. Whatever this area came out to be, as long as b is greater than 1, right? It gets a little crazier if it's less than 1, because notice this goes off to infinity. And that's a question that I can't answer in this course. It's beyond the scope of this course. It requires calculus 2, right? We're only covering calculus 1 in this course. But if you start at 1 and go this direction, however much area is inside of here, right? Think of it as water or some kind of physical space. That is what the value of the natural log is. So for example, if I wanted to know the natural log of 5, right, and I don't have one of these, I don't have a calculator, but I do, so I'm going to do it with a calculator. I would calculate the area from 1 to 5 of 1 over x dx. I would just stop at 5. And whatever area I got, that would be my natural log. All right, I can tell you're all impressed. My comments are blowing up on YouTube. That's your fun fact for the day. So let's do one example. Find the average value of the natural log function on the interval 1 to 5. All right, let's do it. Well, f(av) is 1 over 5 minus 1 times the integral from 1 to 5 of ln of x dx. Using our fun fact, I know that this is the ln of 5. Done. Now, because we have calculators, I don't actually have to draw the graph and measure the area, but I could do the Riemann sum. I could make a bunch of little rectangles and add up the areas of the rectangles. That's the way Riemann would have done it back in the 1700s, because they didn't have these fancy phones or even a primitive form of calculation. Well, they might have had a table, a book where they could look stuff up that other people had already done. All right. Now, I hope you all understand. Oh, sorry. I feel like an idiot now. The function is not ln. The function is 1 over x. Oops. The ln is what you're actually calculating in the final step. So rewind back. The function is there. The natural log is here. It's the picture that I just drew. I should mention, though, just for fun, the integral of ln of x is not easy. If I would have kept that as the integral and the antiderivative of ln of x, that's a whole nother lecture that I'm not prepared to give you today. I'm prepared, but I don't know if you're prepared to listen to another hour of that. So the function is 1 over x, and then the integral is ln of x. All right, so I'm going to get 1/4. And I might point out that if you accidentally do this, that's okay, because the ln of 1 is equal to 0. So if you plug in the 1, it's not going to mess up your answer because the ln of 1 is 0. I was just applying my fun fact, which is that you only need to find the ln of the upper bound, which is 5. So I've got 5. Oh, I could tell I'm getting tired, and I think you could tell too. That's my ln in the modern sense because I have a calculator. 1.609. Blah, 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 divided by 4. And I get 0.4, approximately. So that's my f(av) for this function. The average of the ln is a little bit harder. I might have time to cover it next time, but I really want to get into the business math. I'll leave it to you as a DIY. Well, maybe not. I decided not to do a DIY. I will do it for you. Find the C such that f of C is equal to f(av). So I want 1 over C to be equal to 0.4. I should do a DIY. Solve for C. If I do that for you, you're gonna go, "Why'd you do that, Dr. Jordan? Give us a challenge." So until we meet again, I'm Dr. Jordan, and I'll see you on the internet.